Alright guys, welcome back to Underground Science, and in this video we'll be covering the basic ideas of quantum mechanics. Alright, so let's go ahead and get started. Alright, so let me draw the smiley face for a second. Alright, okay, so quantum numbers has to do with, or not quantum, I just said the answer, crap. So quantum mechanics has to do with quantum numbers. Okay, so pretty much when we talk about quantum mechanics, we focus on the subatomic particles, like mostly on the electrons of an atom, all right? And we focus on many rules, and this everything ties to like electron configurations of different elements, and it all ties to different rules, like we'll cover in the future videos of the Aufbau principle or the Pauli exclusion principle or Pauli exclusion rule, all right? And so that's all. So let me go ahead and start writing down the quantum numbers that we're going to be overviewing in this video, and then in my next video go deeper into that and see how how when we used to get taught that each energy level, like for example the first energy level in like a Bohr model or something, right? So this is the nucleus with its protons and neutrons in it, and then this is the first energy level, and how we said, or we got told that, oh, you can only have 2 electrons here, right? These are my electrons, all right? And then in the second energy level, you can fit 8 electrons. Remember that? Like 8 electrons here. So I'm not going to actually, I mean, you know what, screw it. 1, 2, 3, 4, 5, 6, 7, 8. All right, so we said that we got taught that 8 electrons in the second energy level, and then so on, like 2, 8, 18, 32. That was the pattern. That's how many electrons can fit in each energy level. Well, we can understand exactly why using quantum mechanics and quantum numbers. All right, so things like that we can figure out with quantum mechanics. So let's go ahead and just get the basic overview of what each quantum number is, and then it'll help us in the next video where we talk like deeper about like how to calculate each quantum number and how to know which orbital or subshell we're talking about, and cool things like that. Okay, so let's scroll down a bit. All right, so the first quantum number, guys, we're going to talk about is going to be called the principal quantum number. Okay, the principal. So let me just say number 1. Okay, so what I say? Principal quantum. My U's look like V's, so quantum number, right? Okay, wait, I can't write. All right, principal quantum number. And there's a symbol you could say to denote this. We just say N, okay? So actually, before I go on, it would be helpful to pull up a periodic table, because this has to do a lot with the periodic table also. Okay, so one sec. There you go. All right, so we have a basic periodic table here, right? And so the principal quantum number, guys, is just the energy levels, right? Like we're talking about in the Bohr model. So if we're talking here, this first energy level here would be a principal quantum number of 1. Then the second energy level here would be a principal quantum number of 2, right? So it's just the energy levels, that's it. And in the periodic table, you can also see that right here, this is the first energy level, right? N equals 1. Then this is the second energy level, N equals 2, and so on. It goes all the way down the periodic table, and it just keeps on increasing. That's why we'll talk more about periodic trends and things like that in our future videos. But that's why as you increase in energy levels, right, as you go down the periodic table, you increase the radius of the atoms or the elements, right? So radius increases as you go down. All right, that's just a cool thing. We'll talk more about periodic trends, but let's just write that down since we just talked about it. All right, so radius increases. Or instead of that, let's just straight up put size, because that's if the radius of the whole atom is going to increase, right? If you draw the Bohr model and everything, If the radius increases, that counts as the size increasing. So let's just say size of atom increases, all right, as you go down the periodic table. All right, but that's principal quantum number, right? That's the general overview of that right here. It's all it is just remember N as energy level, all right? So energy level number, you could say. All right, so we're done with principal quantum number for now, right? And we just said it was the energy levels. Now the second quantum number we're gonna focus on it might have more than two names, but what I know, I know two common names of it. It's going to be called the angular momentum quantum number. Hope I spelled that right, quantum number. And it's also called, you'll also see it probably as Azimuthal. I'm pretty sure I'm not pronouncing that right, but hopefully I am. Azimuthal quantum number. All right, and just like our principal quantum number here, we denoted it as N, right? We also have a symbol to denote our angular momentum quantum number, or also called our azimuthal quantum number, right? That's right here, and that's going to be the letter L. Okay, so just like that. That's our symbol for angular momentum quantum number, also called our azimuthal quantum number. Okay, L. So, and this pretty much tells us what subshell it's going to be. So to make more sense of that, it's probably not going to make sense right now, but as we keep on going in my next video, right, if we talk about examples and actually dive into deeper and why everything is, it'll make much more sense, but I'll try to make as much sense as possible right now. So angular momentum quantum number, or azimuthal quantum number, is going to tell us, let's see, what subshell we have, okay, for that element. So what I mean by that is we have, if L is equal to 0, okay, we're talking about the S-subshell, which is just a sphere. Okay, so this is not 3D, but we have a sphere for that if the angular momentum quantum number is 0. Okay, and then if the angular momentum quantum number, or the azimuthal quantum number, is 1, then we have a P-subshell. Okay, so a P-subshell kind of looks like this. All right, no, that's not a good drawing. Let me try again. Okay, so I have to make it equal because I almost drew it like it was hybridized or something. All right, so that's the P-subshell, and then it keeps on going after that. So it actually gets more complicated. The drawing gets more complicated. I'm no way trying to draw those because as you can see, I'm not a good artist, right? So when L equals 2, we're talking about D-subshells, all right, and so on. So it goes like this. Let me write it right now. So this is an S-subshell, this is a P-subshell, and then when L is equal to 2, right? Okay, let me attempt to draw a D-subshell, but it's probably gonna be wrong. So because I'm not good at all. Right, so right here like that, and it's kind of like it's 3D. Okay, so it's kind of like in the back a little, and it also goes like that. Okay, so there's like 4 in here, and then after that I don't even want to try to draw the rest because I'm gonna butcher all of those. But then the F after that gets even complicated. But so let's just state it now. So S subshell, P subshell, and when the angular momentum quantum number is 2, we're working with the D subshell. Okay, and then it goes on like that. So when the angular momentum quantum number is 3, right, we're working with the F subshell, and usually we stop there, right? So we'll just say the F subshell. All right, and again, there's around I think there's 6 of these little subshells in the F subshell, but I'm not a good drawer as it is, so I'm not going to try to draw the F subshell. All right, so we have S, P, D, and F. okay? And maybe you guys might find these familiar, but when we talk about electron configurations, or if you have done electron configurations before, you probably find these subshells familiar, right? When you talk about 1s2, or you talk about 2p6, or you talk about 3d10, right? And then same with F, we have 14 electrons in here, but we'll get into that next video. But this is just the overview, okay? So you can tell what subshells you're going to have, S, P, D, or F, or multiple. There's going to be more than one in each, based on the Azimuthal quantum number, okay? Or the angular momentum quantum number, okay? So just keep that in mind. I think it actually goes on to like G and H and on, but I'm pretty sure it does, okay? But for just the most common is just S, P, D, and F, all right? So that's what we're going to focus on in our future videos also. So that probably didn't make much sense right now because I just stated like just 4 different quantum numbers straight up, or not quantum numbers, but 4 different azimuthal quantum numbers. But I promise I'll make more sense in my next video, okay? So that's our S, P, D, and F subshells, okay? And you can tell that based on the angular momentum quantum number. And now let's move on to our third quantum number. Okay, so our third, okay, never mind, it's not. All right, there you go. Our third quantum number is going to be called our magnetic quantum number, okay? And just like our azimuthal quantum number, we had L, right, to denote it. And just like in our principal quantum number, we had N to denote it. Again, we're going to have a symbol for magnetic quantum number, and that symbol is going to be M with a sub L, okay? So a subscript of an L. And okay, I don't know why I did that in a different color. Let me do it in the same color. ML, okay? And so that's the magnetic quantum number, and the magnetic quantum number tells us the orientations of the specific subshell, okay? So for the S-subshell, since it's just a sphere, right? It's just going to be, there's only one orientation in a 3D graph. So if we had an X, Y, and a Z plane, right? So if we had an X, that's a Y, and an X and a Y and a Z plane like that. So I'm going to label it Y, X, Z. Then a sphere is just going to have one orientation, right? Because it's a sphere, it can't have more than one. And then just like that, if we took a p orbital, then the p orbital has actually 3 different orientations, 3 different p-subshell orientations, okay? We usually denote it as px, py, and pz because it has an orientation on each plane. So let's go ahead and draw that out, right? So let's do a 3D graph, all right? And then let's label our y-axes, our x-axes, and our z, all right? And now that I think about it, right, I just said it has 3 different orientations, our p subshells, right? So we're going to have to draw 3 graphs or it's going to get messy, all right? So let's draw one right here, all right? And let's draw one. Dang it, we ran out of room. So let's just try to squeeze it in. You know what? We're not going to squeeze it in. We'll take our room. All right, we'll do that in the next page. Okay, so we have our y here, our x here, and our z here. Okay, let me actually, let's put the z here so it's not close to the h. All right, so the p orbital will have 3 different p subshells because the magnetic quantum number is going to tell us that. Okay. And again, let's just focus on the overview right now, and let's not focus on how we find it. That's going to be the next video. It's going to make so much sense. Okay, so the p orbital has one orientation on the y-axis, like that. Okay, so that's our one of the p subshells, and this is going to be called our py subshell because it's part of the p orbital, and this p subshell is on the y-axis. All right, and then we're going to have a px subshell, right? So we're going to have a px subshell kind of like this, all right, kind of like that. It's our px subshell, and again, why is it px? Because it's a p subshell on the x-axis, okay? Again, there's 3 different orientations for P, which means we have one more orientation left, and that's our PZ subshell, okay? And our PZ subshell, let's just draw it here, right? It's better to look at it all at once since we're talking about P subshells. Okay, so Y, x-axis, and z-axis, because it's our 3D graph, and then our PZ subshell is just going to be on our z-axis, okay? So same thing right here, here, because this is how we draw our p orbital. All right, so that's right there. So these are our 3 orientations for our p subshells, all right? So p orbital. And remember, we have our s orbital, we have our p orbital, and then we have our d and f and so on. But our d and f orbitals get even more complicated, right? So because our d orbital is not going to have only 3 orientations, it's going to have 5 orientations and 5 of these orientations, and then you can imagine how it's going to get even more complicated. So we'll focus on S, P, D, and F, but for the drawing part, just to get the concept down, we know what we mean by orientations when we talk about different orientations of the P subshells, all right, just orientations in general. At least you get it now. So it's one orientation is going to be on one axis, another on another axis, and so on. Okay, and finally, before we end this video, let's talk about our last quantum number, which is going to be our spin quantum number. All right, so let's go and write that down. Spin quantum number. Spin quantum number. Okay, and just like our previous quantum numbers we've been discussing, we also have a symbol for this, and it's M and a subscript S. All right. So our spin quantum number just pretty much comes in handy when we talk about the Pauli exclusion principle, right? In our future video, we'll talk about more about that when we cover electron configuration, right? But the spin quantum number pretty much tells us the direction of the spin of our electrons, okay? So if there's 2 types, so if our spin quantum number, guys, if it's plus 1/2, it means that it's spinning up, okay? It means that the electron is coming in as spinning up, okay? And this is going to make way more sense when we talk about electron configurations. Like, for example, if we have our 1s orbital here, and we draw our electron configurations like this, right? We draw it like that first. This is our positive 1/2 spin quantum number. And then if we have an element that has both this and this, the last one we draw, so we see that we have 2 electrons in the 1s orbital. This right here is called our electron spinning down, or our minus 1/2 spin quantum number. So those are the 2 types. It can either spin upwards or spin downwards. And we're talking about the electron here. So negative 1/2 spin quantum number is that the electron is spinning down, all right? And pretty much you just have to focus on, when we talk about electron configuration, just know that we have a plus 1/2 and a minus 1/2. And a minus 1/2 is when we draw it like this, and a plus 1/2 spin quantum number is when we draw it like that. Okay, because that's going to come in handy when we talk about electron configurations in a future video. All right, and that's pretty much our overview. Overview of our 4 quantum numbers. And in our next video, we'll dive into more about how to calculate, for example, our Azimuthal quantum number based on our principal quantum number, and then how to calculate our magnetic quantum number based on our Azimuthal quantum number, right? So that we'll just tie it together better. And then we can, in our future videos, we can talk about, based on quantum numbers, again, in the beginning of the video, we'll be talking about why this is, right? Why we have 2 electrons can fit in the first energy level, right? So it goes 2, then 8, then 18, and 32, and then so on. But why is that? Well, we'll figure it out based on quantum numbers, okay? And we'll talk about that. It's going to make so much more sense. Everything's just going to click. It'll be awesome, okay? So hopefully you guys hopefully that made sense to you guys, at least a little. and I hope to see you guys in my next video, where I'll probably be talking about we'll be talking more about quantum numbers. And so don't forget to hit that notification bell so you know when I'm publishing my videos, and don't forget to like and subscribe, or I don't know why I'm saying and, but see you guys next time, all right?